Good afternoon, everyone. I'm Anand Buddhadev. I'm also part of the OARC program committee, and I'll be chairing this next session. A reminder to the speakers, when the timekeeper indicates to you how many minutes are left, this is the number of minutes left to the end of your presentation, excluding question time. So there's 5 minutes for questions at the end of your presentation. A reminder to all of you, please fill out the DNS-OARC survey. That helps the program committee to put together a good program for you. Your feedback is very important to us in determining what kind of presentations we put together for the program. So, for our first presentation for this session, I would like to invite Ulrich Wisser with a presentation title that describes me very aptly, Forever Young.
Thank you, Anand. Of course, we're only thinking of you. And okay. Okay, today I will talk about how to keep your DNS data forever young on the internet. My name is Ulrich Wisser, and I work for the Swedish Internet Foundation. And as part of the DNS team, it is my responsibility to make sure that we deliver fast and reliable services to all users of the .se zone. And yes, so TTL values and RRSIG lifetimes are crucial to our mission, and they have a big influence on our ability to deliver our services. And so that put me on a path to investigate these values, because we actually want to we make sure that we have the right values, and it took me down a rabbit hole that you hope you will follow me today. And so we have 4 main deliverables, and we believe that these will affect the TTL values and the RSIG lifetimes, and I hope at the end of the talk you will agree with me. So the first is we need to have a DDoS defense. And at a former DNS-OARC conference, Giovanni Mura from SRDN Labs showed that longer TTL values will help with the defense against DDoS attacks. And of course, this ability to defend is really essential to keeping .se online at all times. Then, of course, we have a goal of happy users, and happy users usually means faster answers. And the same Giovanni Mura presented at the last DNS-OARC that longer TTL values will keep your data in cache, and that this mechanism can then give you so fast answer that you even beat any cast services. And then we have happy customers, and our customers are registrars, web hosters, and DNS service providers. And they demand faster updates, and they demand faster propagation times over the internet. And that, in other words, means shorter TTL values. And last but not least, we have disaster recovery. And RSIG lifetime and SOA values define the time frame for disaster recovery. And therefore, they are really important to make sure that we, even in times of a crisis, can deliver service to all the users of the .se zone. So, what is the state of the TTL? Well, in these following slides, I will go through TTL values for actually 4 TLDs, and I choose these 4 TLDs carefully because the .eu have actually online updates. So potentially every second they update their zone. .fr updates approximately every 10 minutes. .nl updates every half hour. And at .se, since last year, we update every hour. And so when you look here at the SOA values, you see that none of the SOA values are really that short, like our update cycles. And in case of the SOA record for TLD, that might not be so interesting because, I mean, resolvers are usually not going to ask for it. the SOAR record is mainly used in negative answers, and then it will get the negative, the minimum TTL. But then we go to the NS records and the GLUE records, and these records are delivered by root with usually 2-day TTL. And here you already see that there is differences, and I think most people believe that resolvers are parent-centric. There's still an ongoing discussion about this, but let's see. Here is the question why .eu think that they will change their name servers faster than the GLUE records. But I know, for example, that for .nl they have deliberately changed this to 1 hour for the A records because they want to be able to change A records in when they are under attack, and they want not change names but change A records faster. And then I looked at the TXT records. .eu doesn't have one at the apex, but the other 3s have, and all 3 of us use it actually. We update the TXT record when we update the zone. And here you see that the TTL values of the TXT record not really synchronized with our update times, which is strange if you think about it. And then we have the DNS key, and these are delivered by root. The DS records are delivered by root with a 1-day TTL. And I honestly can't say why .se has 1 hour. I mean, we don't roll our KSK that fast. It's years between rolls, so there's really no need for this. And the best answer I could get for why do you have these values is, yeah, because we always did it that way. I get these answers a lot. So let's look at delegations, and here it gets even stranger. You see that .eu has delegations with 1-day TTL. .fr has 2 days. .nl has 1 hour. That is very close to their update cycle, actually. And at .se, we have 1 day again. Yeah. At least we have the same for the A records. For DS records, somehow at SE we decided again that this should be faster. I don't know. I have really no good explanation, and that is actually what took me down to this look in all these values. And then we have the NSEC records, and this, of course, is the minimum TTL from the SOAR record. And you see here that we're really not preferring update propagation over the internet, and that is something that we have to look into. And then we have these SOAR TTL values, and here we come to a point where we could say that the refresh and the retry value are not so important for TLDs, because obviously we send out notifies whenever we do updates, and so these our slave servers usually won't do a refresh or retry because we are always there. If we are not there, then they're not of much help. But then the expire time is really interesting, and here you see that EU and FR have 1,000 hours. NL has, I think, 30 days, and .SE has 10 days. And we come later back to this together with the RRSIG lifetimes. And then we have the minimum TTL, and here again, it's like the NSEC records that we really not in sync with our update cycles. And so before we make any changes to our TTL values, let's look at negative answers. And so I tried to find some guidance about, what should I choose here. And so I couldn't find much, but so I found a really old RFC, 1033, and it says, at least a day is a good value, and for the minimum TTL. And that, I think, things might have changed since then. So then we have RFC 1912. It says 1 to 5 days are typical values, which is really. And then we have the 2308, which actually defines the negative caching, and it says, no, don't listen to these others. 1 to 3 hours are sensible values. And it even says values exceeding 1 day have been found to be problematic. So I couldn't agree more, but I think that even a value of 1 hour might be too much. And so then we have aggressive NSEC. And just as a short reminder, aggressive NSEC means that the resolver will actually synthesize a negative answer from its cache to a question that it itself has not sent to the authoritative server. And it will do this, of course, with the help of the NSEC records. But there's a few things that the resolver actually needs to do this. And the resolver needs a negative answer in cache. It needs a SOA record with a signature. And it needs an NSEC record to send out. And of course, these 3 records have TTLs. SOA minimum, the SOA record has the SOA TTL value, and then you have the NSEC record, which usually has the SOA minimum TTL value. And these are the values for the .SE zone, which, for example, in this case, would give us a 2-hour caching for negative answers, which in case if you have in a DDoS defense situation is really good, because then for 2 hours, any resolver can actually send out answers without any contact to the authoritative server. But if you look at propagation times for updates, if you now would have a new name in that in the covered space, that would obviously be bad, because now for 2 hours that name is not operational. And so before we make any changes to our DNS, let's look at RRSIG lifetimes. And RRSIG lifetimes, so the lifetime of an RRSIG record is obviously defined in the record itself. It has a time and date when it starts to become valid, and it has a time and a date when it stops to be valid. And the time in between is its lifetime, simple. But usually we don't use the record for all its lifetime. We replace it actually quite fast. So in case of the .SE zone, our SIG records have a 12-day lifetime, and we replace them in the run of 4 days, actually. So there is no our SIG records in our zone that are older than 4 days. And why we do this? Well, if things go sideways, then we have some time left where we have valid signatures in the zone. And if you look on this picture, we have 8 days left that we have all the signatures in the zone are still valid. So, but when we then look at our SOA record, it said 10 days expire time. So if we add the expire time to our refresh time, it means that we will serve the zone to day 14, but that means from day 12 to day 14, we will have validation failures. And not the whole zone will fail at once. There will be a degradation over time. And actually after 4 days, so after day 16, the whole zone would be invalid. And so this is obviously not ideal. Well, what would be reasonable value then? Well, when in doubt, ask your peers. So, and actually our peers, we are a CCTLD, so I looked at, we are very active in the center community, so I thought, well, let's look what the other CCTLDs are doing. And yes, so there's a few of them that have longer RSIG lifetimes, at least longer than what their SOA value is. The problem here is that we really don't know what the refresh time is for the signatures, so we can't actually decide if the SOA expire together with the refresh time actually cover all the lifetime. But, well, at least in the beginning, we see that the lifetime is longer than the expire time. And though they seem to think, at least in the way that we. Then we have people with incredible fast disaster recovery. Andorra, 4 days, is ambitious, I would say. Hungary, I might expect that they cut off a 0 at their SOA expire time and meant 30 days, but who knows? And Lithuania, I just want to go there and see what they're doing that they can recover in one day. Because, yes, and then we have a lot of TLDs that don't believe in DNSSEC or their validation is not used, maybe, I have no idea. But obviously Canada, for example, you see that they intend to serve the .ca zone for 40 days, but only have signatures for 7. So, yeah. But it makes your own domain even go dark. Yeah. And that is signed, isn't it? Yeah. And okay, you could argue that Canada is not signed, but if you look at the last one in the list, Norway, actually Norway is the country with the, I think they are like 80% signed, and they have like all large, they have the largest amount of validation in the world. So for Norway, this obviously should be a problem. And yes, and then I have these where I really could not think of any explanation at all. Maybe somebody's in the room and could explain this, or maybe somebody knows someone. And just as a side note, I don't think any of these values are wrong. I just think that I would like what people were thinking. So in case, to learn something and to make a better informed decisions. And so what is reasonable values? Well, we had these 4 objectives in the beginning, I told you, and so let's see what our 4 objectives told us to do here. And NTHEC TTLs should be SOA minimum, then you always get that automatically from your authoritative. The SOA TTL should be SOA minimum or longer, of course, otherwise you get a really strange caching for your negative answers. And the SOA minimum should be long enough for caching. And that is something that we need to think of very thoroughly, because caching really helps us in case of defense. And we want happy users, which means fast answers. And so here we want our Apex TTLs, we should really look at the parent and see what the parent does. And the SOA minimum should be really considerably shorter than our update times, because otherwise we can't just get the propagation. Delegations should also be really in sync with our update cycles. Otherwise, propagation over the internet is just too short, too slow. And again, we want caching because our users really want fast answers. So, and you see already here there is some conflict between longer TTLs for caching and shorter TTLs for propagation, and we really need to find a balance here. And happy customers, of course, is we want fast propagation, and that means shorter TTLs. And last but not least, we have disaster recovery. And for disaster recovery, we really want that our SOA expire time covers, that our RRSIG lifetime covers the SOA time and the refresh time. And so with that, I'm open for questions.
The expire timer is really only used when you are doing zone transfers to transfer the zones.
Yes.
If you are using other mechanisms, it really doesn't matter.
No, of course not. But that's what we use for, at least from our master out to our.
But that might be the reason why others, have weird expiry timers.
Absolutely. That's why I say I can't say anything what the others do is wrong. I just would, I think it would be interesting to hear arguments about what they're doing, so that informed decisions. Because we all get it that there's no difference between a TTL value of 300 or 299. that is just insignificant. I just, nobody could care. But would be an update, a delegation of 300 or 3,000 BOK. There's arguments to be made, at least at orders of magnitude of TTL values. And
I think kind of aligning the TTLs with the actual update or the cycles that you do, the resigning, makes sense totally.
Yeah.
Thanks.
Cool.
Any more questions for Ulrich?
Okay, thank you.
Thanks, Ulrich. Very much. Our next speaker this afternoon is John Kristoff, and he's going to talk about some threat analysis with IPv6 transition mechanisms. Welcome, John.
Thank you very much, Shumon, for that introduction. I only gave myself 15 minutes, so I'm going to kind of get right into it. But for those of you who know me or knew me at one time, I'm starting to spend more time doing research. I'm doing my PhD now. You may look at my face and my hair, and I'm a little bit older PhD student, but nonetheless, that's happening for me now. But I still work at DePaul University during the day as well. And so I still use that email as my main contact. So this is some work that's trying to get published. It's largely done. It's been done for a little while. The publishing part turns out to be the hard part. So that part is in progress. How many of you remember, just by show of hands, a while back, I think it was Dwayne Wessels who kind of started, did this work initially on something called WPAD. Does that ring any bells for any WPAD? You guys know what that is? So, interesting, and I said, well, what else is like that out there? And there's this other thing that's kind of like it in a way, this thing called ISATAP, and some of you probably know what that is, cringing. And so I went, like Dwayne had registered a bunch of WPAD names, I registered a handful of ISATAP names, and I held on to them for years thinking I would eventually do something like Dwayne did. And about a year or so into my PhD, I had a class where I had to do a research project, and my professor sat down with us, and I had a few ideas, and one of them was, well, I have these ISATAP names, we could maybe do something cool with it. He said, yeah, let's do that. So that's kind of where this started. And it grew into something a little bit more, into something a little bit more general, IPv6 automatic transition mechanisms. And so this is just a taste of that work, ISATAP being a piece of it, but there's a couple of other things here as well. So I'm going to kind of try to take you quickly through some of this. This is roughly the bits I want to try to touch upon as fast as I can. So when we conducted this work, basically we ran through a number of experiments and some research, and we've basically found, from looking at this from a security perspective, these transition mechanisms like ISATAP and 6to4 and Teredo pose a suite of potential security threats. And probably the most generic one through all of them in various forms and fashions is we can hijack people's V6 traffic in some ways, and we don't always have to even be on path to do it. And so we did a bunch of experiments around this, and we found some other things that were quite interesting. And some of you may be on a mailing list that saw something from me recently that has to do with 6to4, which is another piece of this, which I won't talk about now, but we can talk about it offline. So I went and registered a whole bunch of these ISATAP names. So isatap.us, .biz, everything except for .net and .org, because those were registered by one of the people who defined the RFC for ISATAP when it was first standardized. So those are essentially the only three TLDs I don't have. But then there's a handful of dynamic domains that I registered. I did some stuff within our educational institutions. So I've got ISATAP names probably in like 100 different places. So it's a little bit expensive too, by the way. My wife doesn't really appreciate that. But I have a bunch of these names. And then some of this infrastructure, like 6to4 in particular, has what effectively any CAS address is associated with them. And these are prefixes that may or may not exist in the routing tables. And so we took a look at doing some routing table experiments. So I did that. That's not particularly germane to this talk today, but we did some of that stuff. something that's more relevant for today is, okay, what if we make available these names and actually associate them with an actual gateway, so then people do an ISOTAP name lookup, will they actually try to connect to our v4, v6 gateway and route traffic through it? So we did that, and of course, I wouldn't probably be up here if that didn't happen. So yes, we were able to intercept and route traffic for people who were trying to do v6. And then I looked at a bunch of DNS query data that I had from my own authoritative servers for ISOTAP, for our educational institutions, and then I used the DIDL data that DNS-OARC maintains. So that's actually really helpful, and it was actually kind of useful for this project as well. If you haven't looked at that data, it's useful for a lot of things, I think, but it was helpful for this in particular. I'm actually going to skip over the slide. The 6-to-4 stuff is kind of interesting. This is kind of a crummy diagram. We made another one for the paper, and I don't really need to explain this here today. So I'm going to skip over 6-to-4s, and I'll just focus on the ISOTAP piece real quick. So if you don't know, the way ISOTAP works is it's primarily used by Windows machines, but there's clients for other things. And all Windows machines, practically going back to about XP up until just recently, it was installed by default in your Windows machines, and up until recently enabled by default. And what would happen is if you didn't have native v6, you'd issue an ISOTAP dot whatever your default domain was query. If you got an A record response, you would then issue essentially an ICMP exchange, ICMP version 6 router solicitation message, and see if you got a router advertisement back. You're just trying to basically bootstrap with addressing. And if you got that, then you assume that was your ISOTAP default gateway. That's your tunnel. That's your v4 to v6 tunnel, and you try to route traffic through it. Now, the way the happy eyeballs algorithms works, if you've got an ISOTAP tunnel, all your traffic, if you have a v6 destination for it, will take that tunnel over the v4 stuff. If it doesn't work, Windows is pretty good about falling back, but all your v6 traffic would go through that tunnel. So that's kind of how ISOTAP works in a really quick nutshell. If you care, I don't know how well you can make this out. It's a little bit small, but you can look at the slides online. For Windows, this is kind of a rough idea of what it tries to do for v6. If you don't have native v6, it tries a series of alternatives from ISOTAP to 6-to-4 to Teredo. But there's all sorts of ways for us to potentially grab your v6 traffic if it's trying really hard to get a v6 tunnel going. So here's some graphs that we took, and I'll just kind of give you an idea of what we were doing. Don't pay too much attention to these numbers here. If you have particular questions about what we saw, let's talk about it offline. But for instance, the bar chart here on the left, this is just looking at what are the volumes of queries we saw for the different type of mechanisms at either an educational institution versus a cable modem ISP. We tend to see more proportionally ISOTAP queries versus Teredo at the educational institution because we had all public IPv4 addresses there. In the cable modem environment, presumably everyone's behind NATs, and so they were trying to use Teredo more often, which was a mechanism that you'd find if you're stuck behind a NAT. Some of these other graphs are showing just the volume of queries we're getting for our ISOTAP names. Then there's some volume of queries on the different TLDs that we had these in. I happen to have ISOTAP in .uk and .co UK, and Co UK turns out that there's quite a few ISOTAP queries being made out of there. One of the busier TLDs that we actually had, along with one under Brazil as well. So we did some experiments. Because we were seeing people trying to query our names, we could actually set up a tunnel for them. So for those outside of our educational institution, we didn't actually complete the tunnel and allow them to fully use our tunnel to relay all their traffic. We didn't feel that was within our rights to really do that, but we did want to see what they tried to do. So what we ended up doing is we'd say, okay, we'll let them bootstrap, so do the ICMP-v6 exchange to get the addressing. We'll give you an address, and then Windows does this network connectivity test. We make sure that works, and then they will then try to use our tunnel all the time. And so for every connection attempt, they'll send us, whether they're going to Google or whether they're going to their banking website, if it's got a v6 address, they'll try to use our tunnel, but we'll drop everything else. And Windows is very good. If it doesn't actually work through the tunnel, it'll just fall back to v4 really quickly. So we got at least to see the v4 destinations they were trying, a protocol, maybe a port number, but we didn't actually see any data content, any the TCP handshakes didn't complete. So we got a minimal view of what they were trying to do, but we got an idea of what they were trying to do. So these graphs show a little bit of what we saw. So Google and Facebook and all the kind of usual stuff we did see. And I don't think, yeah, so this other graph shows some of the applications and some of the usual stuff you'd expect, like the HTTP traffic. But as we dug through it, and while it wasn't a lot of volume, we saw all kinds of stuff. We saw a lot of DNS traffic going through the tunnel. We saw some SNMP stuff and some telnet stuff. A lot of the stuff that would use these tunnels appeared to be a lot of servers that were set up and default domains and end up using our tunnel. So we saw more or less anything you might imagine. On the authoritative servers for the names that we had registered and were set up to answer queries for, I set up EDNS client subnet on it, which was kind of neat to see. I hadn't really had a chance to play with that before. And so this is just an example of kind of what we saw. So just 3 examples. The top one is just a Google resolver or a Google server giving us the /24 of some other resolver that was looking up an ISATAP name. The middle one was someone in a resolver in Brazil. And it was, behind them was a V6 client actually looking up an ISATAP name. Not sure why a V6 client's actually looking up a name, but it was. And then the last one, we saw a lot of these /32 from China. And this may be well known by some of you, but it wasn't obvious to me. And I thought, why are they giving us /32 ECS data? And it looks like, from what I could tell, because all the Chinese resolvers that were doing this, they all ended in .1. And so I think what was happening here is they're reporting probably a default router gateway address that's not actually the client address. It's my guess. I'm not sure if that's actually true or not. If anyone wants to comment, I'd be happy to hear what you think that is or if you know. So lastly, I hope I'm right around about the time to conclude. I only had 15 minutes. But these are the questions or the thoughts that we had about some of this activity based on this work. I'd recently been doing some work with ICANN, and this came up there, and things like the ISATAP names and other names that Microsoft would use in the operating systems. They would also issue queries for 6to4.ipv6.microsoft.com to locate the 6to4 gateway. They'd also issue a Teredo.ipv6.microsoft.com to look up Teredo gateways. So these hard-coded names, this kind of comes up again and again, starting perhaps at least as far back as Dwayne's WPAD stuff. This seems to be like maybe a bad idea in the general case or many cases. We heard this again today about canary domains. Is that a good idea? I don't know if that's such a great idea. Maybe this might come back to haunt us again at some point. The other thing that, the paper that we wrote, one of the things that we were trying to draw conclusions on was the coupling of domain name systems and IP addresses and the bootstrapping into the routing system or to bootstrap your layer 3. That might not be such a great idea either, right? Maybe decoupling those two in the future if we're ever to do transition mechanisms again. All these transition mechanisms seem to be falling out of favor. They're not completely abandoned. But that was one of the other lessons that we sort of drew. There's lots of queries for all this stuff. So if you haven't looked, like for example, when I looked at the diddle data, the most popular ISATAP name that's looked up is isatap.home. And the reason is that's the most common one is because .home is just a common TLD, but it also doesn't resolve, so resolvers try it over and over again. But what if they didn't? What if some of these TLDs get registered by someone? I'm going to go register isatap.home, I'll tell you that. And that'll add some more data to my experiments. So I'll leave you with some of these questions and thoughts and conclude in hopefully enough time for question and answers if there are any. Any questions or answers?
Thank you, John. Any questions?
NRA Apple. Very interesting research, John. I'm just wondering, when did you take your measurements and experiments? As I have the impression that the problem is going away. Microsoft has disabled the tunnel adapters in latest releases since about a year by default. people
Yes.
start to include 624 and T-radio prefixes in their bogon lists. And when I did some look at recent statistics at, say, high-profile IPv6 vantage points, and what we saw at the time, maybe a month ago, was 0.5% 624, T-radio less than 0.1, and practically no isotype.
Yes.
So I have the impression that this problem, while existent, is going away.
Yes. So there's almost no V6 traffic that uses any of this stuff. 624 a little bit.
Yep.
Almost nothing for ISOTAP or Trano because those are essentially dead. However, and I did see evidence of that. So the measurements that we took, so I looked at the diddle data from 2017 and 2018. I think the 2019 just wasn't ready right at the time I did this. I'm sure it's ready by now, but there was a drop in the query volume a little bit from 2017 to 2018, so it was dropping just at least from there. And some of the query volume, we did this study over probably 9 to 13 months, depending on what we were actually looking at. And the ISOTAP query volume is definitely slowly declining, largely, at least we believe in part, because in the recent Windows 10 release, probably within the last couple of years, they did disable ISOTAP completely. However, there's still, I think the last I looked, there's still all these other Windows machines that haven't been updated that still has this stuff. So there's still plenty of it out there. Now, most of it isn't used because these don't resolve to any address. Same thing with 624 and Windows machines, they don't resolve to any address. But they're there to be used potentially still. So if I add a name and you happen to query for that name and it resolves, then you will use it. So there's still the potential threat, and so that's part of a lot of the research I spent a lot of time previous to my PhD, but still do, is finding these weird things under the rug that just still sort of exist. So this is kind of just a little bit of a theme for me, finding these cobwebs that people have forgotten about. So I don't know if that answers part of your question at least.
Okay, thank you.
Speak of the devil.
Hi, Dwayne Wessels from Farsight. Yeah, so the similarities to the WPAD stuff is kind of spooky, especially given that both of these ideas came out of Microsoft. In the case of WPAD, you know, that was written up as an internet draft, and it never was standardized in RFC. And the draft was very vague about how you stop the domain name searching, right? And so you get a lot of leaks that way. And I'm curious if ISOTAP was the same way. I mean, I assume ISOTAP was a proper RFC. So was it just bad specification, or was it bugs, or is it domain search lists causing this?
So ISOTAP doesn't do that devolved search like WPAD does. It's basically, it'll use your default domain that you're given that your host is already in. So it doesn't do any searching beyond that. So that's kind of good news, I guess. So there is an RFC. I'm not sure I would necessarily classify it as a bug. I think maybe, again, I might suggest that the general lesson of using what is effectively a relative name collision is maybe just a bad idea in general, right?
Yeah.
I think that is maybe a lesson. I don't necessarily would blame anyone for having designed it this way necessarily at the time. And by the way, yes, this particular piece is a Microsoft thing that we saw a lot. There's some other stuff in this research that we did that Microsoft has nothing to do with that's a problem, especially with 624. We could talk about later. Some other vendors got a whack on the head a little bit with that part of it.
Thanks.
Okay, that looks like, oh, thanks.
Thank you very much, John. So this brings us to the end of our standard presentations for this afternoon, and we'll be moving towards the lightning talks. But before we get there, I'd like to remind everyone that if you would like to attend the social event this evening and haven't yet registered, registration is still open. So please do that as soon as possible. And with that, I would like to welcome Paul Hoffman for the first lightning talk. And he's going to talk about some tools from the RSSAC Caucus work parties.
Thank you, Anand. So for those of you, Anand didn't say, but all these lightning talks are 5 minutes or less, and I normally talk too fast anyway, so this should be okay. So for those of you who are not familiar, the RSSAC Caucus is not RSSAC. It is a group of volunteers that RSAC has chosen to do additional work and such like that. I'm a member of the caucus. I'm not a member of RSAC. And so these two tools that I'm talking about are things I've done in the last year for the caucus. So the first one, which is, the first tool is real, the second one isn't yet, you'll see that. So this tool, a lot of people say, oh, well, how do these resolvers work? And especially one of the things we've been hearing today is that different configurations in resolvers can cause the resolvers to do very interesting things. So the design goal here was I was going to make a tool that would allow a researcher to run through, for example, all the open source resolvers, all the versions of bind and unbound and such like that, send queries through them to, controlled authoritative servers, just to, pretty much to watch the PCAPs, see what's going on. So I did that as a test bed. The GitHub is at the bottom there. But basically, you are able to create your own tests. And so, for example, the reason that RSAC had asked RSAC Caucus to work on this was they wanted to see, for example, how do resolvers do priming and repriming? So in order to do that, of course, we couldn't just send things out to the regular routes because we would have to wait 2 days for each one for them to reprime. So this test bed has a whole bunch of VMs in it, one of which are servers that are able to serve the route, but a fake route, with like a 60-second TTL and such like that. So anyways, the whole test bed is there. Everything runs under VirtualBox. So if you're interested in doing this kind of research, within about an hour of setting it up, and there's full instructions and such like that, you should be able, and as long as you have VirtualBox and such, you should be able to start doing things, pick your own open source software and such like that. What I did tentatively is the open source software that's in there is sort of the last rev of each major version. So the last rev of bind 9.10, the last rev of bind 9.11. But you can put anything in there that you want. So if that sounds interesting to you, come and see me, or go look at the GitHub repo. The second project, which hasn't been done because RSAC has not finished, is something the RSAC Caucus was working on in the form of metrics for root servers. And the reason why RSAC Caucus was looking at this was RSAC itself published what's called RSAC 037 last year, which basically says we need to look at the root server system, who should be in it, who shouldn't be in it, such like that. And one of the things that might go with that are some metrics. So RSAC Caucus has almost finished, or has finished their view, but RSAC hasn't finished, a metrics document. And so as we were creating the metrics document, I did a proof of concept implementation for collecting some of this data. If RSAC ends up going forwards and saying, yes, we want an actual initial implementation, I'll be working on that. So there's no GitHub yet, but hopefully that happens and later in the year. And I will do the same thing. It will all be on GitHub, except I'll actually be developing it on GitHub so people can shoot arrows at me during the development process. And I'll announce that on DNS operations and such like that so that people will know about that. So that was it. I think I lightninged.
Thank you, John.
Right.
Sorry,
Is there
Paul.
time for questions?
Yes, we do
Okay.
have time for lightning comments or questions.
A lightning question. Wes Herdiker, ISI. I will talk really fast. The RSSAC Caucus actually has a whole bunch of tools, and they all exist at GitHub/RSSAC Caucus. Can I get you to push yours there too? Was that good?
We talked about that once and you weren't sure. So yeah, so I would imagine if nothing else, we can push a pointer to that.
Okay, yeah, I'll create a repo
Yeah,
for you.
and so just if we still have another 30 seconds, what Wes was saying is that there are other tools that people have created in the past, and they're all in one GitHub, what do you call this, organizations?
Group, yeah, something like that.
Okay, great, thanks.
Thanks, Paul. And for our next lightning talk, we have Shumon Huque, who is going to talk about DNSSEC provisioning with third-party providers.
Okay, thank you, Anand. So I'm Shumon Huque, and I'm going to talk about this topic. I'm channeling Steve Crocker a bit, who I'm going to say is spearheading this initiative with a number of colleagues from the DNS industry, including myself. And what we're trying to do is come up with some ways to improve some aspects of the DNSSEC provisioning ecosystem. All right, so two issues we're looking at. The first one comes up pretty frequently, actually, and this is that when using a third-party DNS provider or operator that is signing the zone for you, there is no well-defined friction-free path today to convey the DS record up all the way up to the registry. Now, some CCTLDs are using mechanisms like RFC 8078, which is CDNS key, but there doesn't seem to be any indication yet of widespread adoption of this mechanism. So we may need to come up with new methods to augment the system. And importantly, I want to state that we are trying to accommodate solutions for most use cases, so ranging from the non-technical registrant that may have very little clue about what DNSSEC actually is, all the way to the sophisticated enterprise. The second issue is a little bit newer, and that is the situation where multiple distinct DNS operators are cooperatively serving the same zone, signing and serving the same zone data. So the general scheme for doing this is already defined in a document, multi-signer DNSSEC models, but there's follow-up work that could be done and that people are interested in. So, for example, there is no well-defined protocol today for the providers today to directly communicate and coordinate the key sharing and cross-signing, etc. So this slide I'm essentially going to gloss over. I'm just listing the main actors and the functional roles that they play in the ecosystem today, and who may be impacted and who may need to be involved in some of the solutions that we come up with. So regarding conveying a new DS record, there are a number of possibilities, of course. So there's the pull model, which has already been defined in RFC 8078, but we think there's work that could possibly be done to extend the push model, and we want to figure out, is there a way to involve the DNS operator directly in this mechanism in a more meaningful and more automated way. And some of the possible work that could happen in this area is, for example, formally designating the DNS operator in the RRR system, the use of delegated authorization schemes, whereby the DNS operator can act on behalf of the registrant for performing some limited, well-defined scoped functions such as DS updates and things of that nature. So this diagram just talks about some of the possible models and which directions the workflow goes that we've thought about. There's more, I don't have time to talk about this right now, but in the appendix to this deck, we sketch out some of the models in more detail. And the cross-signing part with multi-signer DNSSEC, today at least, the cross-signing involves the registrant or the zone owner in some kind of coordination activity. Sometimes it's done manually. And what we're thinking of is extending the protocol so that the DNS providers themselves can run a protocol between themselves that can coordinate some of this stuff. And so this is my last slide, I think. We have a mailing list. It's called DNSSEC Provisioning at shunkuro.com. So if you'd like to join us, you can email Steve Crocker at steve@shunkuro.com. We are looking for a few more DNS providers and registrars, and even registries, actually. And I want to give a brief advertisement for a DNSSEC provisioning panel on this topic that will be convened at the upcoming ICANN meeting in Cancun next month. And Steve, I think, is moderating that panel. And lastly, there's a few people, if you want to talk to us here, we're on site, a few people already involved, so I'm going to name them, and if you could raise your hand and identify yourself. Paul Ebersman, I see. And Gavin Brown is here somewhere. Where is he? All the way over there. So you can come up and talk to us, and we can fill you in and let us know how to participate. And do we have time for questions? Okay.
John Reed, Akamai. How does this relate to the DNS op draft? Is this an extension of that? Is this?
Yeah, I would say it's probably follow-on work for that. So originally when we were developing that draft, so you're talking about the multi-sign models draft, right? So we actually had a section in that talking about inter-provider handoff and developing some mechanisms to kind of make this more automated and smooth, where the operator had an active role. In the end, we decided to take that out because it sounded like more work than we needed to do to get this out of the door. And so that may still happen in a follow-up draft. But in the meantime, I think it's important to at least convene the principal set of actors that can actually make a workable solution in this space and get them talking, and then figure out where there are points of agreement, how we can move forward. Once we've determined that, I think we can write a specification.
So closer to actual implementation and details and all that?
Yeah,
Okay,
yeah,
great.
that's right.
Paul Ebersman, Neustar. Just as a follow-on with that, part of why we're trying to get as many different operators, registries, registrars, and the rest is there are ICANN contracts, other contracts, all sorts of other things beyond the technology that have complicated the issue. So that's why we're sort of taking it offline and solving that problem outside the draft, I think.
Yeah, that's a good point, Paul. I mean, you're totally right. I mean, some people will often come up and says, why doesn't everyone just deploy CDS and CDNS key and we're done with it? But I mean, really, it's not entirely a technical problem. There are business models and interests that have to be accommodated. And frankly, we need to understand and get those players involved. Okay, I think that's it for me. Thank you.
Thank you, Shumon. Our next speaker is Paul Vixie, and he's going to talk about DNS Operator Feedback on Fujiwara-san's draft about avoiding fragmentation.
Thank you very much. I've got 3 topics that I'm going to jam into about 6 minutes, which means I'm going to do a poor job. But I am going to be here through the social and through the rest of the night, so I'm really trying to preload the schedule for all the things that we should be talking about once this thing ends. So first, Fujiwara-san decided that he would write a draft to try to describe what it is that the so-called Flag Day will do in October, and actually make it a change to the protocol, or at least change the recommendations on how it's operated. He signed me on as a co-author because I sent him quite a bit of feedback. I'm really trying to incentivize all of you. Please read the draft. It's going to expire in March, which means that we're going to be posting an update. We'd like to get it adopted. We'd like to turn it into what the community believes should be done. Right now, it probably represents a little bit too strongly what I think should be done or what Fujiwara thinks should be done. We did, however, get some operator feedback from somebody who, this is a very abbreviated version of the comment. I find it amazing that somebody knows that they're using DNSSEC, they're doing it on purpose, and they can tell when it's not working. I think that's a major milestone. Given that this is not, one of the normal people who would be in this room, because all of you fit that qualification, but there's some selection bias on getting into this room. I find it interesting that this operator cares a lot about TCP state. And I think our answer on that has to be, and I'm asking you for guidance on this, has to be, we've done web service with a massive amount, gigabytes, tens of gigabytes of kernel memory for TCP state on the web, and it's not even all that expensive. So you probably need that anyway, and right now they are only allowing TCP on IPv6, and they say that's working fine, but I can tell you they're not getting very much IPv6, so the fraction that is TCP is so small that of course they wouldn't worry. If V6 takes off, they're going to have to turn it off. They'll be turning off TCP. So they really don't want to do that. The other answer to give is, well, most of the things that you're worrying about here are things that you can avoid by not implementing this particular recommendation. In other words, you're an authority server, so just leave eDNS buffer size the way it is and offer TCP and do all those things. However, what's clear from this is that the messaging is weak and that we need at least another page of text describing use cases and describing various operator roles for stub resolvers, recursive resolvers, and authorities. So if you have, it can't be down to 2 already. Sorry. No, sorry. All right, moving right on. We have been using 1,500 byte MTUs ever since the mid-'80s when we got 10 megabit Ethernet. And the number of packets per second that we're seeing on even a 10 gigabit link, let alone a 400 gigabit link, is insane because of that maximum not changing. So we used to get about 14,000 packets per second on 10 meg Ethernet if they were minimum sized back-to-back minimum spaced packets. And 10 gig, we're getting 14 million. At 100 gig, we're going to get 140 million. That's a lot of packets. And I got to say that where the bits per second scales with circuit density, how small can you make your components and how closely can you put them to each other, the packets per second does not. It scales with the power, the heat, and the complexity, which means that we are inevitably going to have to raise the MTU. We're not going to get to 10 terabit or 40 terabit networks with packets that won't fit in a single electron or something like that. We're just going to run out. So this is inevitable. We should probably have already been at around 64K by now. And you are all in a position to know how hard that is because path MTU discovery doesn't work. We're going to have to do something. And we should be doing it now because the underlying protocols don't permit greater than 2 to the 16th. And we're going to be changing those in our lifetime is what I think. I believe we're going to see multi-megabyte packet sizes on networks 30 years from now. And I realize that's insane, but that's where we're going. That's, the scale requires a certain amount of compromise. And I'm not asking for path MTU discovery. If you just look at your own route, it's got an MTU. If you're using your gateway route, it's probably going to say 1,500. But if you're using something in your LAN or your metropolitan network or your company network, it might be 64K. And that would be enough. And we have to look at that even though it's hard and we don't get paid more for solving that problem. Now let me talk to you about this 1232 thing. A lot of folks have said that 1232 is the V6 equivalent to 576. It's not. The way that we got 576 is to first determine 68, which is 60 bytes of IP header. That's if all the options are used, HLN 5, no, HLN 15, whatever it is. The maximum sized IP packet is 60. The minimum sized IP payload is an ICMP header, which is 8. And so 68 is the minimum size, and that's the actual IP version 4 MTU. You could, potentially have to fragment a 576 byte IP packet into 68-bit chunks. That was what they were thinking, and that's what the spec still allows. So then we took that 68, added it to 512 as a nice convenient, gee, that's the size of a page on my disk drive, and said that is the minimum reassembly capacity that you are expecting the other end to have. If they can't reassemble at least a packet of 576, they can't speak on the internet. That's what that means. That's very different from what 1280 and 1232 all mean. 1280 is the established minimum MTU. It is more like 68 than it is like 576. And it's a lot bigger than 68, but it's still not as big as it could be. So right now we're having a big discussion around what to do in October and whether we should be just everybody defaulting to 1232. Let me tell you why that's a bad idea. It doesn't leave any room for IP version 6 extensions, whereas the IP number of 68 presumes all extensions are present or all possible options are there. This presumes none. And it turns out that the IP extensions are not all that uncommon. And so whereas TCP knows its available space because it's already built the IP or IPv6 header, and it's already built the TCP header, and it already knows everything it needs to know how much is left. And then it'll just pull a certain amount out of the reliable stream and make a segment out of it. That's because it's kernel resident. We're not. We're name servers. We don't know how big the IP or IP6 header is going to be. And the quick people are now pushing for UDP options as a possibility. So 8 may not be a good assumption on the size of a UDP header for very many more years. What that means is we have to guess how many payload bytes we have. And if we guess 1232, then that is only going to work if there are no extensions or if there are no actual MTU 1280 links between us and the destination. So I want to say those are bad assumptions. The actual MTU is 1500. That is what you can fit, and the way I know that is because people sending 1232 byte packets never have a problem doing it. And that would not be working in today's internet if the actual MTU weren't more like 1500 than it is like 1280. It's time to be honest about that. And I think that what that means is that we should leave some room for tunnels, because our packets are going to get encapsulated by somebody, and leave some room for IP extension headers, and that's around 100. So we need to assume that it's about 1,500 is what we really have, and about 100 is what we really ought to leave on the table for people above us in the stack, or below, depending on how you count. And so I'm currently recommending around 1,400. This matter is a discussion item in the Fujiwara draft. It will be discussed in the DNSOP working group if they decide to adopt that draft and turn it into what the community wants. I am really trying to get you to talk to me about it today and read the draft. Thank you.
Thank you, Paul. Thanks, Paul. Our next speaker is Suzanne Woolf, and she's going to talk about algorithm rollover in .org.
Thanks, Anand. Hi, I'm Suzanne. I work for PIR, and we're the folks responsible for .org. As part of our operational maintenance of the zone, we manage the DNSSEC signing parameters, and it's time to revisit some of those. And one of the things we need to do this year, we hope, is take a look at the current signing parameters, decide whether we need some updates, decide how we want to evolve what we're doing. And since we are internet people, we're looking for ways both to benefit from the experience of others who have done updates of DNSSEC signing parameters for your zones, and also we want to make sure that we are sharing as much of our experience as we can to benefit others. So the basic technical characteristics of the zone, 10 million names, one of the larger TLDs. The first one signed in 2009 with SHA-1 and NSEC3 opt-out. Our back-end registry services are supplied by Affiliates, have been since the beginning. They do the technical operations, including the DNSSEC signing. We're working together on planning and execution. We've done this before. So, the bases are covered, but we're looking for additional insight. We'd like to do the roll this year, but we have no urgency about it if that turns out not to be the right way to go about it. If it turns out we need to take longer, we will. We have some basic technical decisions that, again, that were last made in 2009 that we need to review and revisit. Algorithm choice, obviously SHA-1 is over. There's been some actually discussion on the mailing list about, getting rid of SHA-1, we're doing that. Do we want to go with algorithm 8, algorithm 13? Is NSEC3 with opt-out still the best choice for what we need? There is, somebody pointed out to me yesterday, an NSEC3 dependency on SHA-1, but we have to decide how much zone walking actually matters to us. Is there a concern about size of the zone or signing time if we lose opt-out? so on. But these are the basic sort of technical parameters we are willing to revisit and change if that improves the situation. So what input are we looking for? We want to talk to DNS validator vendors and operators to help us test and to help ensure that we have strong operational contact during the key events of the role so we know what's happening and if there are issues developing. We are interested in hearing from researchers who want to have data, want to measure what happens when a very large zone changes some of these parameters. And we're looking for experience about timelines. You know, again, we would like to do this year, but if there turns out there would be a reason why it needs to take longer, we'll do that. And we're just looking for advice from others' experience. How do we make sure that we're providing the most transparency we can in our planning and our execution? What should we plan to share? What would benefit others from our experience of doing this? You know, where to find, it would be, it's either me or Joe Abley, our CTO. And when Joe and I were talking about what this presentation should be, he said, look, the message here is we want to do this the internet way, not from the basement of some ivory tower. So we're looking for your input. And I think that's less than 5 minutes.
Great. Thank you, Suzanne. Oh, I'll allow one question or comment.
I was this close.
Hi.
Sure, what do you need?
This is Ulrich from .se. So obviously we have done a role.
Yes.
2 years ago. Actually, yeah, I'm happy to tell whatever we did. And then I would be really interested in what you think of the changing NSEC, because we do also run .nu, and we're doing NSEC 3. Mm-hmm. And everybody tells me, oh, if you want to do NSEC, it's just changing. But nobody has ever done it.
Yeah.
And that would be really interesting because, I mean, we publish our zones, so we obviously don't need NSEC 3.
Right.
And,
well, and this is, in fact, one of the things, like I said, this is one of the things we have to revisit.
Yeah.
Do we just go to NSEC?
But I have really no idea how to change NSEC algorithm.
Okay. Well, then we should have some further discussion and hear from anybody who does have the direct experience, preferably without too many scars. Thanks.
Thank you very much, Suzanne. Our next speaker is Ed Lewis, who is going to talk about DNS houses. Welcome, Ed.
Hello again. So what I have here is a talk fragment. One of the things I do quite often is I look at observations of what's going on the internet. I try different types of statistics, gathering, and different questions out there. In fact, I have charts from 2 different talks in here. But one thing I'm going to focus here is something called DNS Houses. And the title here is actually incorrect. I'll explain that in a second. So the idea here is that I do lots of different work out there, and when I take these observations, I don't like to name names. I don't like to rank individual items for one reason or another. Sometimes it's misleading, and sometimes it just comes up wrong if you say who's doing what. But I want to still get some meaning out of the internet. What's going on with the packets? What do you see out there? And in particular, I discovered that if you understand how the operations of the internet are co-hosted or co-located, you can find out places where if one engineer makes a decision and they run one zone, you might see one thing go left to right. But if that same engineer is working for a large organization, one little tick might influence 250 zones. But that doesn't make the second one any more impactful. You really want to, it was still one decision made by one person or one committee, and you really want to get into this when you start doing the analysis here. So I come up with this idea, I call them DNS houses. You look at all the TLD, and if you look at TLDs, picture them this way, a lot of places, TLDs might be managed in buckets. It might have 6 of them, might have 250 of them, and they might be GTLDs or CCTLDs, and I divide them this way because the policies for each are a little bit different. So how do you determine a house? And this is how I think about doing this. One is you could go out and ask all the operators, you operate this TLD, what other ones do you do? Now, they may not want to answer that. I don't like doing surveys. They take long. They're usually out of date pretty quickly. So I like try to find something that's more automatic out there. One thing I've been using is I use the R name in the SOA record. For those of you who don't know the SOA record by heart, we have the M name, the master server. R name is a responsible name for that. It's supposed to point to the RP record. And when I mentioned this in one of my meetings, first thing I heard was, well, you can't trust the R name. It's totally arbitrary. It turns out that when I do this in some cases, it actually gives me some useful information. And for the TLDs, it seems to be pretty good. And some in the reverse map of the DNS also. So I could also do the NS set. I tried that. It's a little more bulky out there, but that gives me some hints. Or I could look at the IP address. There are ways to figure out who's doing what on the internet. And you just try to use that to find out what's the structure of the internet. So this is from one of the talks I'm not giving this time around. And this is an example of what comes out of here. I have the top 13 operators counting by DNS zone. And I'm afraid I don't have a mouse to point here. And this is a sea of numbers. I like this stuff. It's better than graphs for me. Number one is the number one TLD operator out there, runs 241 GTLD zones. Only GTLDs. They went into there. They were invested in that area. But what I have in these other columns, I have servers. They use 4 NS records. The NS records for the NS set for each of their zones is identical. They use just 4 of them. And they have 8 addresses, 1 v4, 1 v6 address, and they have so many routes. And I was doing this in a support of a ROA coverage test, and they have all of those recovered by ROA. I'm not going to go through all the lines here, but the top couple are interesting. Operators 2 and 3, you can see they have CCTLDs and GTLDs. They do both. And this starts giving you a hint that sometimes the CCTLD world and GTLD world are not completely separate. They work together. Operator number 5 is an RAR. This is actually not TLD. This is also the reverse map. It has 102 reverse map zones. That refers to delegations out of IP6 ARPA or in out of ARPA. And you can see up and down the line, the number of servers used, the number of names, they vary. It gives you a different idea what their policies are. For operator number 3, they usually use 6 NS records per name server, or per zone. And if you multiply 6 times the number of zones, you get almost the right number there, 964. Sometimes, for some reason, it's off by 2. But they have done that everywhere. They use the same idea of 6 unique names for each zone. They're kind of vanity names. The second chart here, this is the same chart but filtered, so to speak. On the first chart, it didn't see very many CCTLDs. So this one shows all of the top operators that have CCTLDs, more than 2 of them. And you notice that, also note the chart's not very long. This is everyone above 2 CCTLDs. The long tail from there goes pretty far out, but we have a lot of combining of authorities into a few houses. And to give you an idea, I've used this for another purpose. That was for looking at RPKI coverage of routes. This was from a talk that was talking about DNSSEC adoption in the CCTLD space. And I did the same thing here. The numbers are a little bit different because different set of data, different way I added things up. But I have the operators down there, the total TLDs, and again, non-CCTLD is the way I call it that time versus CCTLD. What's interesting to me is the last column. It just shows in DNSSEC world, there's only 1 unsigned zone run by any of these top TLD houses out there. Which, the amazing thing is there's about 200, or 150 to 200 TLDs not yet signed. Of that 150, only 1 is run by a large house. That means all the other ones are run by individual houses. Which means for those who want to go out and do deployment, you've got a lot of walking to do from house to house. And that's kind of what this kind of helps you focus is what efforts need to push things through the rest of the system out there. So if anyone has any comments about how to divide this up into houses, I'm interested in that because I'm still working on the studies that I'm using this in. And also what you can find out from this is really interesting, and I'd like to talk to people about that if they want to. And hopefully at some point I'll have enough to put into a real talk. Okay, this is a lightning talk, no offense. Into a longer talk about a particular topic somewhere. So with that. Yep.
Thanks, Ed. We don't really have any time for questions or comments, so we're going to move on. Our final speaker for this session is Brian Dickson from GoDaddy, and he's going to talk about DOT, our favorite topic.
Okay, hi. So this is some stuff I've been working on, not directly in my day job role, but with support of GoDaddy. I'm interested in finding out if we want to actually have clients that want to be able to do upgrade to the regular resolvers, but doing it up to encrypted using DOT. What's the roadblocks and how can we do it? So that's what this is about. There's two sets of presentation materials. One is the slides for me just jabbering very quickly. The other is a much longer set of slides that are a little bit better. And there's also a proof of concept up on GitHub that can be downloaded and played around with. So the basic issue is there's a couple of standards for client to resolver privacy. They all both use TLS. There's DOE and DOT. DOE 53 uses IP addresses, not names. So how can a client upgrade to DOT? The objective here that I'm trying to do, come up with a solution for upgrade to DOT without selecting a different resolver. And the problems are basically DNS resolvers don't require a name, a DNS FQDN, but for TLS, a server name is actually mandatory. You can't use an IP address, you have to use a name. Public CAs limit you, they have to be public DNS names. The number of CAs that you need for validation is large. The signing process for signing a certificate is complex. The lifetime is an issue, could be purchases, and then there's the validation of the request being done by the CA. So it pretty much rules out using CAs for that simply because of these restrictions. Some partial solution ideas, DANE, TLSA, for certificates, which lets you publish fingerprints in DNS. And that allows you to do private CA usage or self-signed certificates, but it does require DNSSEC. And the question about where you can publish this stuff, Roy Aarons has a great proposal on using ISO 3361-1 reserved two-letter codes. The one I'm picking up on is ZZ or ZZ. Forwarders complicate the whole thing because if a client talks to a forwarder and then the forwarder talks to the resolver, if the client wants to learn about the resolver, there's no direct communication from the client to the resolver. You can't use eDNS. So the result is you have to use in-band with DNS queries and responses for that communication. That's actually not a horrible thing. If you publish information in DNS on the same resolver, so the same resolver is publishing information on itself, about itself, that solves a client reachability issue. It's in-band. It's compatible with private use, and the resolver's name is the name of the DNS zone. There's reserved space. You can serve it authoritatively on the resolver, and the only things that can reach it, or that are guaranteed to be able to reach it, are the resolver's clients. That's actually a really positive thing. And you can do TLSA in that, signed with DNSSEC. You still have the issues of trust anchors. There is a bootstrap aspect to it, but the resolver would need to have two zones that it would serve. One is a well-known zone, which is necessary to bootstrap the whole process, and the second would be a unique name for the resolver itself, which would be a unique name within that private space. I'm suggesting using something that's got a lot of entropy. A 12-character name from base 32 hex gives you about a trillion names, so collisions are unlikely. Locally significant, but globally unique, no collisions. Using the resolver name .arpa, that's the suggested name that I came up with, would let you bootstrap the whole process. You would do a bootstrap using the trust anchor for resolver name .arpa, do it once, use that to get to the trust anchor for the unique name. Once you have that, then everything else you can get is going to be DNSSEC signed, gets you a TLSA record, then you can get other information out of that. And effectively, you have all the information you need to validate the TLS cert, actually make the communication. You already know the name of the resolver. You're able to get there. And that gets you to DNS over TLS to the resolver, with or without a forwarder in the middle. Some additional things this actually facilitates or is compatible with would be using a private CA for a centrally managed certs and centrally managed zones. That would be usable in the case of a franchise, or no CA but managed trust anchor. So you have a centralized trust anchor assigning at KSK for all the resolver name.arpa instances. That would let you do head office, branch office with independent local operations within the branch offices, but you're still controlling it centrally. And then there's some additional things. You can make it more complex for handling forwarders that upgrade that would otherwise blind the actual discovery using resolver name.arpa. And this goes into the different issues that can show up in that. To do that, you would add a server function and some upstream information for the forwarders, and the proof of concept. That's up there now. It can be downloaded and used. It uses loopback addresses only, builds a bunch of different instances, and launches them within a particular proof of concept model, and you can play with it. Questions or comments? I know it's lightning, but.
Tom Pusateri. I remember Martin Thompson talking about this and, at IETF, and he said there's no problem issuing certificates for IP addresses. And there's actually quite a few, not everyone will issue them, but there are quite a few places that will issue them directly.
Understood, but this bypasses that as being an issue and provides other benefits.
Hey, Matt Poundset. I think if you're trying to specify a globally unique name in sort of user-defined address space, you're going to run into problems. Unless you're also defining a registry somewhere?
No, it's just globally unique by accident.
Yeah.
i.e. the namespace is so gigantic that if you collide, it's got to be by design, not by accident.
Except that I think what you're going to find if people actually start using this is that they're going to use natural language names in there, which are almost certainly going to collide.
Oh, no, I'm specifying as part of the standard random. Has to be random.
Yeah, okay. Yeah, I'm not sure how much people will stick to that just because it's in the specification.
Yeah. It can be explained to them, you use random or you run significant risk. And I also include stuff about don't reuse names, don't reuse keys, don't reuse anything.
Great. Thank you very much, Brian.
Okay.
Right, so that brings us to the end of the lightning talks for this afternoon. And I have a number of announcements. The first one is that if you want to go to the social event, please register. If you haven't already done that, registrations are still open. You will need to wear your badge to the social event, so please make sure to take it with you. The social event has drinks and finger food, but there's no actual dinner. You can have your dinner later. For those who are attending the EDDI event tomorrow morning, you'll need to keep your badges. There's a sticker on your badge, so please take that with you. And EDDI is now full, so you cannot register for it. For those of you who are attending the OARC Roundtable event tomorrow afternoon, you will also need your badges, so please keep them. There are still some spaces remaining if you wish to register for the Roundtable event. Tomorrow, between EDDI and the Roundtable event, there is no lunch. It's a DIY, do-it-yourself lunch, so you can go out and get something. Dinesh tells me that there's a very nice food cart just outside selling South Indian dosas. So give that a try. And there will be coffee breaks in those events tomorrow. And if you wish, you may keep your lanyards with you. You don't have to return them. And please take your badges with you if you like. If you return them, they will just go into a bin and your personal data may be visible to other people. A reminder to fill in the survey because that helps the OARC program committee prepare a good program for you in the future, and the feedback is always very valuable. Then, the next OARC workshop is going to be held in Paris, OARC 33, next to IDS. So please register for that. And OARC is looking for sponsors for this event in Paris. So if anyone is thinking about sponsorship, please speak to Dinesh or any one of the OARC staff. And OARC is also looking for patrons for 2020. So again, please speak to Dinesh or any of the OARC staff about this. So that's my announcements done. I'm now going to hand over the mic to Suzanne, who would like to say something about Bill Manning.
Wow, and I didn't. This is lots harder than getting up here and talking about DNSSEC. And I won't take too long here, but many of us here knew Bill Manning, some of us for a very long time, as a friend and a colleague. And he was very much a part of the DNS and networking communities. And I believe most people have heard by now he passed a couple of weeks ago. And because he was a colleague to so many of us, because he was so much a part of the communities that are here for OARC and Nano this week, some of his friends wanted to have a little bit of, have an event, just a remembrance for him. Primarily thanks to Louis Lee, who actually did something about this idea. We've got a room reserved tomorrow evening from 7 to 9 at Perry's, which is a bar a few steps away. We'll be able to have, some snacks, some drinks, and share some memories of a unique person. If you want to be there, there's actually an invitation page on Facebook that Louis Lee put up, or just see me and I'll get you on the list. Please do RSVP if you plan to be there, because we do have limited space. The other thing is that so far it's me and Louis handing credit cards to the bar. So we'd appreciate any help, but that's the important thing, is that show up, share some memories, be there for our friend. Thanks.
All right, and so first of all, some thanks out to everybody. Thanks to all of you for attending. This is what makes these meetings worthwhile. I'm seeing everybody here. The speakers who come with their own volition and on their own dime to share their knowledge with us. The PC, as usual, did a great job. We have the volunteers and the full-time DNS-OARC staff, who I think have done a great job with the conference. And of course, I'd like to thank our sponsors, VeriSign, as patron, and Comcast for the event. And the last thing before we head off, have a little something. Dave Lawrence, would you pop in up here? So many of us have known Dave for a number of years, more usually as Tail than Dave, but he has been an active member in our community and had a couple of years with our board doing an awful lot of work for OARC. And so in recognition of that, we are presenting him with a plaque.
Thank you.
And thank you for your time with us. And that concludes this OARC.